Okay, so welcome back to the last class of the series as per our academic calendar. So, today I'll note down all the problems that did exist in our methodology so far. So, this was my general representation of any problem, of course, the state space where there are some obstacles like this. The agent has to go from a source to a goal, and the actions were stochastic in nature. Now, previously we made into ridiculous assumptions, and those were bad assumptions. The first one was that I assumed that the model is known. And what was the model? The model was probability of reaching the state S dash given from state S, I apply action A, where this specifically was assuming the Markov decision process. So my probability only depends, my probability of reaching S dash only depends upon the current state S and the action taken A and nothing else, which is a fair assumption. But then the problem is, how do I know this model? Now, we deal with robotics. The manufacturer does not give anything called as a model that, gentlemen, here are the probabilities, go fit in, do your value iteration, policy iteration. We don't get these probabilities. And if we don't get these probabilities, how are we gonna even try out solving for the stochastic action? And the second is that for any problem, my state space is very large. So when we started, I gave you some interesting problems to solve as a lab exercise, and even with good heuristics, you couldn't get timely results. And that was when you were not even visiting the complete space. Today we're talking about not just agent moving in a grid like this, we're talking about complicated games, all those video games, huge maps, and a lot of things that the players can do, opponents doing things around. The state space cannot be visited in full. We're talking about the robots which have so many degrees of freedom acting in this wonderful world. Even a fraction of the state space cannot even be visited. So these are huge problems. So even a linear algorithm for the state space is not possible. And because it's not possible, how will we do value iteration or policy iteration when even a linear state space visit is not possible? So we'll very briefly try to solve it under a chapter name called as reinforcement learning. And what's learning already covered in a sister code. So I'll take in their ideas of learning and I will put that down over here, and we'll see how do we solve this problem. Definitions first. So what's reinforcement learning? A reinforcement learning is a special kind of learning where, as I keep on visiting things, acting in a real world, acting in a simulator, I keep on getting something called as a reward. Previously we modeled it also like this. And because I keep on getting a reward, all that I want to say is high rewards the nicer things that I'm doing, bad rewards, the worst thing that I'm doing. So, a reinforcement learning is a learning where you aim and learn to take actions that maximize your rewards. Fair enough. So, a learning is supervised when you know the exact target. So, somebody tells you for this situation, this is the best action possible. Somebody sitting by your side, somebody teaching you the video game tells you this input, this is what needs to be done. That's the best action. That's supervised learning. Unsupervised learning is when you only know the inputs, so you try to find out what are the patterns, what are the commonly occurring things, and that's all. Later on, of course, you need the output, so you'll go to someone whom you think is the best player of that game and you'll say these are the common things which are happening. So somebody will say, yes, for this situation you do this, for this situation you do that. Simple enough. It's reinforcement when you get the immediate feedback, but you don't know what's the correct answer. You only know whether what you did was good or bad. If it was good, do more of it. If it was bad, do less of it. And you keep on acting by trying to maximize the goods. Another major difference. So, supervised learning, primarily we talk about things which are episodic. That's the input. So you got the X-ray. Is that X-ray of a coronavirus infected person? You make a decision, that's all. Or for something like a game, you just say that, okay, for this state did I make the best move, that's all. You don't consider anything before it, after it. Unsupervised, exactly the same. Or you say this is the input, to which cluster does it belong. Reinforcement, we're looking at sequential things. Like the last example, you're undergoing a lot of pain, you're still doing it, you keep on getting pains. You're still taking pains because you know that even though reward is negative, your machine learning system in your head still says that it's good because only by all these pains you'll get the golden reward at the end, which is positive. So reinforcement learning is sequential in nature. Even though something has smaller reward, you keep on doing it, expecting a bigger one at the end. Classic example. So I'm teaching you something. So one way I could teach you is that I give you a question, you all solve it up and give it back to me. And what I do is I tell you that this is the correct answer. So many people, I cannot correct all the copies. I give you the correct answer. You look at it. Okay, that's the model answer. That's my answer. This is where I get wrong. And you inscribe it in your brains. That's supervised. Another thing is what many people asked me to do. Give us all the question papers that you've taken in the past for this course. And then what do people do is, okay, 2014 question paper, 2015, 16, 17, 18, 19, 20. And then you say, okay, these are the commonly occurring questions. So definitely what 75% of the marks will be out of this. Unsupervised learning, you only have the inputs. Of course, you go to the class topper and say, give us the answers. The class topper gives you answers. You put it in all your chits. Online exams, you even put it in front of your system and just start writing. Reinforcement is, I give you a question. You give me answer. I give you marks. I don't tell you why are you wrong. I don't tell you whether you're wrong. But looking at the marks, looking at others' marks, you know how is it going. Nobody may have the perfect answer, nobody may get full marks, but you know what are better, and then you try to answer it next time the same question comes in similar lines, do something and try to see if you can do something better. That's reinforcement learning. So learning how to walk, you collide, you get pains, bad to do, you fall down, something bad, you walk, you take a step, wonderful. So those are the things that you need to do more, and that's the kind of learning that we will be looking at this time. So let's start small, and for now let me forget this problem and only solve for this problem. So I need to adapt the value iteration. State space is small as of now. I need to adapt the value iteration. I need to adapt the policy iteration such that the equations do not have a probability term inside them. So how do I do? My first idea, so idea one. So what do I do? Value iteration, policy iteration, excellent algorithms. And because they are excellent algorithms, therefore I leave them intact. What's the problem? I don't have the model, I don't have the probabilities, so I learn PS dash given SA. And how do I learn? From S, I make the robot take action A multiple times. So 100 times I make the robot stand at S, take the action A, and I look at whether it reached here, 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 here. Where did it reach? So probability if S dash given SA is from state S, I took the action A, how many times did it reach S dash? Divided by from state, how many times I took the action A. Simple. And practically what you need to do is, you need to play this game of going to goal randomly, 100 times, 1,000 times. I don't know how will you get volunteers to play games like this, which is just reaching the goal. Interesting games, you get many people. I will volunteer. The work description is play games all day, all night. So you could write in randomized algorithms that do that, and whenever from state S a person takes the action A, which is up, and reaches a state S dash slipped, you just do a database entry of this thing. So number of times from state S, A, S dash was reached, new value is old value plus 1 stored in a database, and you calculate this probability values. The problem is that you'll have to play games too many number of times. So every SAS dash, you need at least 150 to 200 trials. So the total number of trials becomes this 200 times the number of SAS dash possible. In the worst case, the state space size squared, because it's S and S dash, it's one of the any states possible. This one is one of any states possible. So capital S squared times number of actions times 200 times each. Very, very large number. So we had problem with policy iteration. There was too much of state space. This is the same problem. Very, very large number. And therefore, I'll try to do something which probably is different. So let's have idea number 2. This one is not very appealing. So idea number 2 is, I try to ask myself, eventually I need to calculate this and this. I need to calculate what's the utility of S and I need to calculate what is the policy, what's the best action at state S. And you know that if I calculate the utilities last lecture, I can get this one up. So my problem is, how do I calculate utility? Can I define utility again intuitively? So the utility of S is, from S, I keep on taking actions as per the best policy. I eventually go to a goal. The problem is, every time I'll get a different path. And because every time I get a different path, my problem was that how do I calculate the utility? So suppose this time I get a reward something, 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 something. I say R1 plus gamma times R2 plus gamma square times R3. The total reward becomes as R of the first part that I get. Similarly, I get R of the second part that I get, R of the third part that I get, and so on and so forth. I take it for 1000 parts and I take the average. And because I take the average, this is by definition what is my utility. So again, absolutely simple, and the absolute simple thing is keep playing this game day and night, day and night, day and night. When you reach the goal, for every state that you visited, calculate from that state till the goal how much is the total reward that you get. Make a database entry. That is an indicative utility of that state. From that state till the goal, how much is the total reward that I got? That's an indicative utility. And for every state, just take the average. Play it day and night. And once you play it day and night, then you get a lot of entries inside it. However, again, for every state S, you will have to probably simulate it many times to get a reliable estimate. And because of that, it's too many simulations. And because it's too many simulations, it's too many computing problems. And therefore, I will say let's neglect it up as well. So I don't like it. Let's neglect that up.